Hi students, today in this session we are going to discuss about the properties of pyridine. So already in the last two classes we have discussed about the physical and chemical properties of pyrrole and thiophene. So in this session we are going to discuss the physical and chemical properties of pyridine. So in the first physical properties, pyridine is a colorless liquid, a colorless liquid. And actually in our lab, if we see, it is available in a small light pale color, in a light pale color, because sometimes it may undergo some kind of oxidation. So that's why it is available in a light pale, or it is actually a colorless liquid. And if you come to its smell or odor, it has a fishy odor. It has a fishy odor. So the fish smell. And it is also miscible in water. So it is one of the rare quality. It is miscible in water, and it is one of the very good organic solvent that you already know, and it is very important. Miscible solvent, it is one of the very important miscible in water, miscible solvent in water. Yeah, miscible in water or miscible solvent in water. And it is one of the very important industrial solvent, very important industrial solvent in organic chemistry. And if you see its boiling point, the boiling point is about 115 degrees centigrade, around 112 to 116 degrees centigrade, which is the boiling point of the pyridine. Pyridine can be stable, okay, it is not much volatile. So this is about the some physical properties of pyridine. Now we'll see the chemical properties of pyridine, means that is the reactions of pyridine. In chemical properties of pyridine, we may see so many number of reactions, but this electrophilic substitution reaction is one of the property for a criteria of the aromaticity we'll see in the pyridine. As you all know, as we already discussed when we discussed about the aromaticity of pyridine, the pyridine is not easily undergoing or readily undergoing the electrophilic substitution reactions, but still at vigorous conditions, at contrast temperature, high pressure, at that situation even pyridine also undergo some electrophilic substitution reactions. So before the electrophilic substitution reactions, let us see which position of the pyridine is more preferred for the electrophilic substitution, where the electrophile can be attacked. So if you see the structure of pyridine, it is almost similar to the structure of benzene, where just there is a replacement of a nitrogen with the carbon. So that's why even if you see its physical properties also, it shows many of the reactions similar to the benzene. So most of the properties are similar to the benzene. So even chemical reactions also similar to benzene. So here in the nitrogen, the position 1, 2, 3, 4, 5, 6, all these carbons have hydrogen. So these hydrogen can be replaced with an electrophile. So such type of reactions are electrophilic substitution reactions. So in this case, you see there is second and sixth carbons are equivalent. They have same properties, second and sixth. The same way, third and fifth are also having same. They are equivalent. The fourth is the different, fourth one. So there are three positions we may see where the electrophile can easily be attacked. So second or sixth, third or fifth, or the fourth one. So these three positions. Let us see which position of the pyridine, which position in the pyridine is more preferred for the attack of the electrophile. So let us see now the electrophilic attack at second or fifth or sixth position, third or fifth position, or at the fourth position. We'll see now electrophilic attack at second or sixth position. So this is pyridine. Okay. Now when an electrophile is introduced, it is going to attack at the second position now. So we'll get a carbocation. The electrophile has been introduced at the second or sixth position. So here at the third position we get the carbocation. The remaining is same. So this carbocation can be, it is an unstable intermediate which can be stabilized by resonance. If you see its resonance structure, these pair of pi electrons will be shifted here. So there is a creation of a double bond, and this positive charge will shift from this position to the fifth position. The electrophile, hydrogen. Here also hydrogen, there is one hydrogen. Each carbon has one hydrogen. So here the positive charge is shifted. It became a double bond. Here also double bond. So now this double bond will shift here. So there is a formation of a double bond, and the positive charge will shift to the nitrogen atom. See, this is happening. Electrophile, hydrogen. Yeah, there is a formation of a double bond here, and the positive charge come over the nitrogen. So in the last, this hydrogen will be giving its electron and forming a double bond, and it will be eliminated. So these three are the resonance structures. With the elimination of the proton, it is going to form a electrophile substituted pyridine. The electrophile is at the second position. So this is 2 substituted pyridine. So at second position we have an electrophile, 2 substituted pyridine. Okay. Here we are forming 3 resonance structures. These 3 are the resonance structure formed when an electrophile attack at the second position of the pyridine. Okay. So let us see now the electrophilic attack at the third position. Electrophilic attack at third position. Third and fifth are equivalent, so I can write third or fifth position. Both are same. Yeah. So this is pyridine. Okay. Here now when an electrophile is introduced, so it is going to attack at the third position. So let us see the carbocation intermediate formed when electrophile attacks. So electrophile shifted here, attacked here, and there is hydrogen. The positive charge come at the second position with the hydrogen. The remaining is same. So this carbocation also can be stabilized by resonance. Let us see its resonance structure. These pair of electrons will shift here in formation of a, not here, yes, here. These pairs will shift here. So here there is a formation of a double bond, and the positive charge will come over on the nitrogen atom. Let us see that. No, not positive charge. Sorry, positive charge come over at this carbon. So these electrons will be shifting here, and the positive charge will shift here to this carbon, the carbon number 6th. Is the formation of a new double bond, and the positive charge come over at this position. Here, not here, here. The electrophile and hydrogen. Now this can also be stabilized by resonance. These electron will shift here, and this forming a double bond here, and there is a formation of a positive, the creation of this positive charge at the carbon number 4. Yes. Finally, this hydrogen will give its electron, forming a double bond, and it is eliminating. So here the proton elimination we'll see. When proton eliminated, it is going to form a 3 substituted third position. There is a electrophile. There is an electrophile is been substituted. So this one is the substitution at a second one, 3 substituted pyridine. Here also we found 3 resonance structures. Here also we found 3 resonance structures. As you already know, when a carbocation gives more number of resonance structure, that will be a stable one, and that will be the preferred one for the electrophilic attack. When in second position and the third position, we get the same number of resonance structures. Now we'll see the electrophilic attack at fourth position. So this is pyridine. When an electrophile has been introduced, so this pi electron will take that electrophile, and now the electrophile, this is a proton, and the positive charge will be forming at this position. Double bond, double bond. Okay, this carbocation can be stabilized by resonance, so this will give electron. As it is an intermediate, I am putting it in a square bracket. It is unstable one. So now here it has become a double bond, and the positive charge will shift to the nitrogen atom. This hydrogen electrophile, this become double bond, and the positive charge over the nitrogen. And this is also show another structure, resonance. This electron will shift now and become double bond, and the positive charge shift from this nitrogen to carbon number 2 or third position. Yeah, the positive charge, it became double bond is earlier as it is. Yes, this is the third resonance structure. No more resonance structure here. Now this hydrogen will give electron, and with the elimination of this proton, it is going to form 4 substituted pyridine. So this is the product. Sorry, I'm not much comfortable at below portion to write. That's why these structures are not exactly the same. Yeah, no, electrophile. This is 4 substituted pyridine. Yeah. Yes, here also we got again 3 resonance structures. 3 resonance structures. Here also 3. In case of pyridine, an electrophile attack at second, third or fourth position, we got the same number of resonance structures. It was easier to find out which is the most preferred position in case of purine and pyrrole, because there we used to get 3 and 2 structures. The which one gives the more resonance structure, which will be that would be the most stable structure, and that would be giving the electrophile. So at that position, electrophile used to attack with stability. But here if you see all the positions, whether second position, third position or fourth position, all of them are giving 3 resonance structures. So now we have to see the stability of these resonance structures. So when electrophile attack at the second position or sixth position, so here carbocation, here also carbocation, but the third one, this structure has the nitrogen with the positive charge. As you all know, nitrogen is an electronegative element which cannot hold positive charge. So that's why this resonance structure will become unstable. Unstable. So the stability, resonance stability, will be only by these two structures. So in the case of electrophile, when attacks at third position or fifth position, if you see here, there is a carbocation, here also carbocation, and here also carbocation. All three are stabilized here by resonance. And okay, and when the electrophile attack at the fourth position, see here there is a carbocation, here there is a nitrogen with positive charge. So again the same, so when nitrogen has a positive charge, so it is an electronegative element, hence this structure also become unstable. Okay, and this one is again carbocation, it could be stabilized by this resonance. So now you can say which position is most preferred. Yes, the third or fifth position is the most preferred position for the electrophilic attack in the case of pyridine, because all three structures give carbocation which can be resonance stabilized, and here we got the three structures. Here we only get two stable structures, here also we got only two stable structure. Hence the electrophilic substitution, if attacks if it takes place in the case of pyridine, that will be only at the third position. Okay, because the pyridine is not readily undergoing the electrophilic substitution. So here the third position is the most priority, it gets the highest priority, or it is only the position where we can find the electrophilic attack, because these two will give a and one unstable structures. So the third position is the preferred structure, preferred attack, preferred position for the electrophilic attack. Now we will see the examples of electrophilic substitution reactions. So as pyridine is not easily undergoing electrophilic substitution reactions, we cannot see all the kind of electrophilic substitution reactions. Very few reactions can be possible. We will see nitration and halogenation, two reactions. And these are very important for 4 marks in your exam. Please note them down, because this much if you write, you will get definitely the all 4 marks. Now we'll see the examples, nitration and halogenation. Now we'll see nitration. Here the nitronium electrophile, that is NO2 plus, will replace the proton. So here the pyridine undergoes nitration when it is treated with KNO3, potassium nitrate salt. Here we do not require HNO3, because HNO3 is not much concentrated like salt, so that's why we are getting a concentrated salt like potassium nitrate, and it is treated with sulfuric acid, which also catalyze the reaction. Okay, the mixture of potassium nitrate and sulfuric acid has been used, and this is heated to 300 degrees centigrade. As we already know, pyridine not readily undergoing this electrophilic substitution reactions, so we need to heat this reaction to 300 degrees centigrade. Then only there is the electrophilic substitution takes place at third position. Yes, that is nitrate, NO2, 3 nitro pyridine. As you already earlier seen in case of furan and pyrrole, the reaction used to take place in a cold condition, because they both are readily undergoing electrophilic substitution reaction. Here we need to heat. That's why at vigorous condition only the pyridine undergoes electrophilic substitution reaction. So pyridine undergoes nitration by using potassium nitrate in concentrated sulfuric acid when it is heated at 300 degrees centigrade to give 3 nitropyridine. Yes. So now we'll see another example, that is halogenation. The one thing you need to notice that the pyridine does not undergo chlorination. No chlorination here, because already seen chlorination in the case of furan and pyrrole, especially in the case of pyrrole, all positions used to get the chlorine radical, sorry, chlorine electrophile, that is chloronium electrophile. But here this chlorination is not possible, as it is not easily undergoing the reaction. But we can do bromination, because bromination is also an example of halogenation. In case of bromination, pyridine may undergo bromination. Okay, pyridine undergo bromination. Okay, so when pyridine is reacted with bromine, here this reaction is very slow. So it will take around 2 days to complete the reaction. 2 days, about 48 to 50 hours it needs for the reaction to complete. It's a very slow reaction. There, in the case of pyrrole and uh, furan, we could do it in a minutes, but here it will take around more than 2 days, 48 to 50 hours. But the reaction takes place and we get the 3 substituted bromine derivative of pyridine, that is 3 bromo pyridine, 3 bromo pyridine, pyridine to 3 bromo pyridine. So pyridine undergoes bromination with bromine, and that reaction takes place for about 48 to 50 hours. Then we'll get 3 bromo pyridine. But though reaction takes place, this yield of the reaction is very much poor. Whether in case of nitration or in bromination, the yield will be very poor yield. Around maximum around 30 to 40% we can get the product. Here also poor yield, there also poor yield, is very much poor, because it is not suitable. The pyridine is not easily, or it is not suitably undergoing this electrophilic substitution. These reactions are not suitable for the pyridine. So we know the reasons, right? The one is this nitrogen is a electronegative element which pulls all the electron towards it and making the benzene ring with a partial positive charge. So that is what benzene ring itself is electrophilic. So there is no reaction. How the reaction takes place between electrophile. So that's why. So one thing, electrophile cannot attack the benzene ring when pyridine is there, when nitrogen is there. And another reason, this lone pair are free electrons on the nitrogen, so those will attack this, those will be attacked by the electrophile, hence it is going to form pyridinium ion. Instead of the substitution reaction, there is an addition reaction, okay, at the nitrogen may takes place. So this is about the examples of electrophilic substitution reactions, nitration and bromination we can see. Thank you for watching. Please like my videos, please watch completely, then only you will get the complete idea about the topics, and please subscribe my channel. Thank you.